Welcome everyone. We're very happy to have Sunjin Choi from IPMU, and he's going to give us a set of three lectures, textbooks lectures about uh, homology and other things. And this first lecture is going to be about proving easiest quantum gravity from gauge states. Over to you.
Okay, I would like to first thank for giving me a chance to speak at this wonderful place. So in these three lecture series, I would like to produce some holographic approach of studying quantum gravity from boundary gauge theories. I will focus on in particular, I will focus on the BPS sector of body enclosed for UN nodes, which is due to cyclic string theory in AdS5 X S5. In fact, when I first tried to prepare for this lecture series, I plan to focus on one subject and to give a successive lecture series, but then for some reason I changed my mind. I think mainly because most of you are very familiar with this index and cohomology business, and some of you are collaborators, some of you are working with this. So I changed my mind, and I in these three lecture series, I will illustrate three different but related approaches to studying the AdS gravity from boundary gauge theories. So my first part today's talk is about settlements of the index of enclosed force by nodes in Lagrangian limits, which will be due to the black holes in AdS5 X S5. And tomorrow I will talk about the forecharge cohomologies of enclosed force by nodes, which are due to some black microstates in AdS5. And finally, I would like in the final lecture I would like to put some new ingredients in the bulk AdS5, which is nothing but the orbital singularities, and see what is the implication of this from the boundaries bulk quantum. So before going to the main part of today's talk, I will give very general introduction to make sure that all of you are on the same stage. So in the success, so I will introduce most of the notations and conventions, so you can follow easily in the successive lectures.
Let me just say that the comments you made at the beginning got me right. Don't overestimate at least some of the audience. So the simpler starting point, the better for some of us. Then you can wrap up it. Thank you.
Okay, so as I said, we want to study the quantum gravity on AdS from the boundary gauge theory, meaning that we want to utilize the AdS correspondence, which states nothing but the quantum gravity in antidisperse spacetime, which is, you can think of nothing but as some covariant bands, is holographically described by conformal field theory on the boundary. And one of the most famous and the example of the successive lecture series will be the quantum gravity on a vertical AdS5 X S5 due to four-dimensional n-equals force for symmetry UN Yang-Mills theory. And as is well known, the semi-classical gravity in the bulk is emergent when safety dual has large degrees of freedom and is strongly coupled. So both of them are a bit difficult to analyze, but I will illustrate how can we study this kind of gauge series. So let me first tell you some basic ingredients of 40 inputs for spine middle. So it has KSU 2,2/4 symmetry. The bosonic subgroup of it is nothing but the SO4,2 conformal group times SO6 R symmetry. And you have 16 planetary supercharges, 16 conformal supercharges. And in all the talks, I will only focus on the radially quantized setup of n-equals for spine mode. So we put the theory on S3 times R, meaning that the states on S3 will be there will be one-to-one map between states on S3 and the operators on R4. And we will denote the SO for rotation symmetry on S3 the curtain charges of vessel rotation symmetry as J1, J2. So this is nothing but the rotation on 1-2 plane and 3-4 plane. And we'll denote R1, R2, R3 as the curtain charges of SO6R symmetry. But sometimes I will use some notation there. Sometimes I will put Q. So anyway, so in the radially quantized setup, the conformal supercharges and Poincare supercharges are Hermitian conjugate to each other. And for the field contents, we have 6 scalars, fermions, and gauge field. So this is the basic ingredient for the N equals first by mils. And we'll focus on the so-called 16 BPS sectors of this N equals first by mils, meaning that we want to analyze the operators annihilated by our chosen supercharge, Poincare supercharge, and its Hermitian conjugates. And these two chosen supercharges satisfy the superconformal algebra given by this. So they are nilpotent operators and give you these. So the 16 BPS operator will have vanishing this combination of charges, so it will satisfy this BPS condition, which states that energy equals to the summation of R charges and angular momentum. Then, since we pick certain supercharges, you can consider some commenting subgroup. In full superconformal group, this is given by SU 1,2/3. And you have some formula generators inside of this group. And in the free theory, you can write down the elementary fields, which is annihilated by these supercharges. Then you will find 3 scalars, 3 Carolinos, 2 gauginos, and the anti-self-dual component of the field strengths, and you can add arbitrary number of holomorphic derivative. So from these letters, you can construct general gauge invariant local BPS operators in the fluid theory. This is the general introduction about N equals first by mils. And any questions about this notation?
What do you mean by free BPS letters? Sorry, I'm not sure.
You can just consider the Yang theory in the free theory limit, G to 0, and just consider the elementary fields annihilated by QM.
Okay. To preserve the condition.
Yeah. But if you turn on the coupling, they might not satisfy the condition.
Yeah. And the letters, because they're adjoint fields, they're not by themselves gauge invariant.
Yeah. So at this moment, people
sometimes use the word words for the gauge invariant.
Yeah.
And multi-words, multi-traces are sentences.
Is that right?
I think that's something we try to use as well.
At this point, as I said, I will focus on the BPS sector. Maybe some people will complain that BPS sector will be too trivial, but actually it is not true. So you can see that even in the BPS sector, there are states with indefinitely large energy. There is no upper limit on the energies on 3 sphere. And also, furthermore, you can consider the non-trivial thermodynamic ensemble using R charges and angular momentum. So you can consider some thermodynamic partition function. And in the dual gravity side, in this sector, you will find some supersymmetric black holes in AdS5.
Sorry, can I just ask? So those free BPS letters, will they preserve that symmetry, the U1 plus SU2R plus SU3?
Yeah.
They do this, right? Because they commute with the charges and okay. Thank you.
They transform and represent.
They transform as represent. That's what I was trying to decide. Sorry.
Actually,
Okay. They transform as no, just because the 4th index, I thought, for example, SU3R might be preserved or something. No.
They transform and
sorry. This M is the SU3R index, and this alpha that is SU2.
Okay. So they actually transform. So once you start exciting with them, you'll just break.
You see, these letters are annihilated by the special supercharge. These other supersymmetries are these other symmetries are those that commute with us. So these letters that are annihilated by carrying zero charge and the transform is representations of them.
Okay, yeah, that's true. They will. Okay, fine. Thank you.
Okay, and also if you consider the supersymmetric black holes in this sector, then it will carry electric charges and angular momenta, but you unrefine all of them. You can treat this one chemical potential as taking the role of temperature or inverse temperature in the BPS sector. And in terms of this inverse temperature or temperature, you can draw the figure like this. So this is roughly the energy of the black holes, and this is a temperature. And you will find the small black hole branch and large black hole branch, and you can compute the free energy of these black holes in terms of temperature. And you will find the famous Hawking phase transition between thermal gas of BPS gravitons and supersymmetric black holes. So supersymmetric black holes behave very similar to the usual Schwarzschild black holes. So there are some non-trivial thermodynamics in this section.
Wait, sorry,
Yeah.
just
Yeah.
so this is you're looking just at Lorentzian. These chemical potentials are real?
Yeah.
Okay, so the zero temperature limit of Lorentzian black holes. And you say you look at one parameter set. This one parameter set is both J is equal and all three Q is equal.
Yeah.
And you're looking at what these axes are, Q versus IS.
So there's some energy, you can consider it as energy of the supersymmetric black hole.
Right, so it's one parameter set, so therefore it has both definite charge as well as a definite chemical potential.
Yeah.
And you're plotting chemical potential versus, and you're seeing there's a first order effect. Somehow I didn't even know this. Okay.
Sorry, just slow it down. So the first line is delta and omega, the second line is only omega. So these black holes correspond to the same chemical potential, is it? You looked at a smaller set, huh?
I only find all the chemical potential to see the one parameter set.
Is that needed for supersymmetry? For that would
No. This preserves for symmetries, but just for illustration purposes. Yeah.
But it's sort of needed if you want to use black holes. Because let's say we're going to set all three charges, all three Q's equal, and both J's equal. So you might have thought there would be a two-parameter set of supersymmetric black holes labeled by these J and Q. But as you know, there's only a one-parameter set of supersymmetric. Supersymmetric black holes in space of extreme black holes are codimension one. So if you wanted to have a one-parameter set of black holes, then you're going to take one cut of this. That's somehow you couldn't have drawn this in a two-dimension.
Right. Okay, so you're forced to do this
In some way, if you want to compare with normal black holes.
No, not your. Not your.
Yeah.
Okay, I got it. And this is so I observed it like for the finite temperature, there's a small black hole and a large one.
Yeah, this is the analogous behavior to the AdS black holes, this finite temperature phase.
And the right hand side is computed, the Hawking page is computed analytically, like
Yeah. And exactly precisely computed, let's say the Hawking page temperature.
It's just where this quantity goes negative, right? Log of this quantity goes negative.
Yeah.
So what's the y-axis of the right side?
This free energy of the black holes or on-shell action. Okay,
So if there was a way of computing this quantity directly, we should see a phase transition. We don't know of a way of computing this quantity directly.
the field theory, yes, we can compute. I mean,
Without a -1 to the f?
No.
This quantity is hard to compute, right?
But I thought if it's supersymmetric, please forgive me, but whether you add the -1 to the f or not doesn't make a difference. Convenient numbers. Slightly. I see. Yeah. It makes sense. Sorry. All states contribute in this object, not without the organ state.
There's one very stark difference. Sorry to stop. Just one, just in front of you may assume we all know too much. Okay, there's one very stark difference, which is when you put the -1 to the f and you want it to be supersymmetric, you have to have a one-parameter restriction on it.
Yeah.
Okay. Whereas this quantity, as Sunjin said, was supersymmetric for both these. So that tells you that you lose information by going to -1. This quantity is mine. I mean, even apart from the fact that they may be cancelled, small cancellation. This quantity calculates the number of states along a line in charge space. So the index calculates the number of states along a line in charge space. But this quantity calculates the number of states at a point. So very, very different.
Just reading what's going, but I mean, sometimes like Ashok in his n equals 2 work argues that the black hole entropy computes the index.
Yeah.
But that's not true here. I guess from what you all are saying, right? So, okay.
Who should say? I mean, you should say.
Yeah, the situation is a bit different. So when Ashok analyze such black holes and illusory computation, it's what black hole is in the flat space time, and you can use some isometries of black holes so that the photon cancellation cannot do very important role in computing such index. But now we are putting the black holes in the antidistor spacetime, curved spacetime, and same logic cannot be used. And there are many Bose-Forming cancellations and oscillations and so on. So you will see what's the result of what's the implementation.
It's not just there's cancellation, just the bosonic fields.
Yeah.
I mean, at least some decoupling we know of it explicitly.
Yeah.
And just one more comment about that. Ashok, what Ashok did was go to the near horizon of the black hole.
Yeah.
Okay. So what he did was to compute all the states that you could associate with, that entropy.
Yes.
Okay. And this situation, at least if our gray galaxy story is correct, that does not compute all the states. Because there are a significant number of states outside.
Yeah.
So it qualitatively might be.
Yes. And even in this cut where they have a regular black hole, apparently it doesn't.
Now here there it may.
Yes.
Maybe true. There's this beautiful story, right, by Benini and friends about the attractor and so on. Maybe.
There are some stories, but these are necessary for taking black holes. So, but its logic is weak.
The expectation is that at large n this is true.
Yeah, large.
Yeah, we know that there are minus ones all over the place in the weak coupling set. So how can this be true?
How can what be? So suppose you've got things in charge. You've got a line in charge space. The black hole's at one point in that one point has either j equals half integer or integer. So at that one point, it's either bosonic or fermionic. So if you could manage to zero in on that one thing, it could be true. Because there is this very interesting story that they had, right, where they try to identify a particular linear combination of these five cartons as the R symmetry that appears in this emergent superatom, and demand that it be annihilated by that combination, and that gives some interesting stuff. So I feel that there may be a story.
So the thing is that
it's not worked out properly.
In the Ashok sense analysis, as you said, all the states you can treat it as boson, right? But here you will see that depends on the charges, boson fermion domination will be oscillating. And I think the main reason why such oscillation appears is that because of the black hole in the cover space and it necessarily rotates, that's the topology changes.
Just one last word about that. What's really important here is that these black holes, like other black holes, like flat space black holes, have a large emergent superalgebra. The black holes themselves preserve two supercharges. But you go to the near horizon geometry, that doubles. That's four supercharges. So that's the power. That's what you're going to use if you're going to use it. And I feel that the previous stories, people have said something.
Yeah, this is a supersymmetric black holes. Unrefined all the chemical things is one parameter, but you may ask that what if you have two parameters, right? Then maybe one nice guess is that this supersymmetric black holes will be similar to like charged AdS black holes, right? So in fact that's true, although it is not published anywhere, but in one of my notes, I found that this when you refine two chemical potentials, so you now consider the supersymmetric black holes having different charges, and you introduce chemical potential for the difference of charges. And then you will see that it behaves very analogous to those the charged AdS black holes. When you see the charged AdS black holes, you can draw some phase diagram in terms of temperature and charge. And if it has finite charge, you can see the first order phase transition between two black holes phase transition, and there is a critical point where the second order phase transition happens. And you can see exactly the same behavior from the supersymmetric black holes, even in this case. You can also compute the critical exponent, and they are the same. So these supersymmetric black holes behave really similar to those finite temperature black holes.
But this whole story is in chemical potential space. Right?
Yeah,
You just look in terms of charges, everything is smooth. It's not no phase transition.
So yeah, and one other thing we can say is that there is the recent work of Shiraz, even in the supersymmetric sector, the black holes exhibit some thermodynamic instabilities, which is reminiscent of some dynamic instabilities of finite temperature like sporadic instabilities, and you can make airy black holes utilizing these instabilities. So as said, there are even in the supersymmetric sector, there are many non-trivial thermodynamics, which itself is very interesting, and also it gives some lessons towards the finite temperature black holes. So it is worth to study.
Can you just go back to the previous slide? If you look, can I just ask something, which is, if you look at the extremal black holes here, I mean, are they supersymmetric? They do preserve some supersymmetry, right? Mm-hmm. And then I don't know this.
This is just charged. Charged extremal black holes don't preserve any source. Start with no.
Oh yeah, sorry, yeah.
I see. You're turning on a J and so on, but it doesn't matter.
No, he was giving an analogy.
Yeah. But take your case where you have omega and delta. Presumably you get a similar phase diagram. Therefore, you have the analog of extremal black holes. Or am I wrong about that?
No, there is nothing.
Oh, there's no line there.
Yeah.
Okay, that's what I wanted to ask. If you had, because then there'll be all the super Schwarzschild and so on to help you. And I wanted to ask whether this is
super Schwarz.
This is super Schwarz.
All of these black holes have AdS.
In the near horizon you have super Schwarz.
And you preserve supersymmetric omega and delta.
This preserves super.
And now, just to you'll tell me later, but with the super Schwarzschild play and so on, can you do more just in terms of counting all the states from the near horizon? Because now double, you have a sort of infinite dimensional.
Using the super Schwarzschild modes in the near horizon geometry, you can count the states of supersymmetric black holes in usual way for this normal case. But
presumably for yours too, right?
But I don't think that will also apply for the gray galaxy.
No. The gray, I mean,
this normal supersymmetric black holes, they work well.
So what can so you can go beyond classically, you're saying you can get the one loop, one loop. Has more been done? For instance, maybe Sandeep's question is going along the lines of, can we do exact calculations by local laser?
I don't know how far they go, but as far as I know, they compute one loop result, and
I see, it's not one loop exact, because the Schwarzschild path integral is one loop exact, but it's not one loop exact. I know some years work.
No, it's one loop exact, but you can have some non-perturbative corrections on top of that, and that I don't know how much they compute.
Or is it hair or something? I don't know. Sometimes it's all of that other junk, right?
Yeah. Okay. So certainly there will be gravitons outside.
Okay.
So I emphasize that because even in the supersymmetric sector, there are really interesting physics. So,
but just coming back to something, that's sort of interesting, right? Because the one loop Schwarzschild is doing stuff in the near horizon. There are the gravitons outside, which at least in the gray galaxy.
Then I don't think we can account for such things from the near horizon geometry.
Probably not. But is there still a sharp separation? Can we still do this plus that? Mm-hmm. Or is there some transition region stuff? Sounds interesting.
Yeah.
But you know, when you get this superstructure modes from this neo-horizon geometry, basically what people are doing is that starting from this full AdS black holes, you integrate out all the fire modes, right? But if you have some gravitons very outside, then it'll be very tricky to what do you mean by integrate out and get all the neo-horizon.
Yeah, so you shouldn't integrate that. You should just compute the whole determinant.
Yeah.
The whole determinant will have a path from outside, we certainly know that. And a path from inside. And there may be some interaction between them.
Yeah.
It sounds interesting, right? It sounds like more than what people normally do with the Schwarzschild slurry. And a very controlled set.
And just to say one more small thing, sorry, I know nothing about this, but please, the beautiful thing about Ashok's calculations was that he formulated the quantum, entropy function, which was just defined in AdS2, right? And all of these recent developments take one step forward in that they keep the near horizon AdS2, right? And there's a very precise formulation as the Schwarzschild. So, he does the extremal calculation exactly, Ashok, in his entropy function. That's what I thought, at least. But if it can be taken to the next step where you can cleanly separate, like you say.
Yeah, I feel that there are gravitons outside as well.
Yeah, there will be.
So you want to, they will contribute, these will contribute.
Yeah.
But maybe there's some.
You can't decouple.
Maybe.
Yeah,
there's some region in the middle, right? There's the trunk, there's a deep throat, there's the deep AdS, then there's something in the middle.
Yeah, maybe. Yeah, I don't know. Maybe you should introduce some other interactions in structure.
It's practical because it's just a question of computing a determinant.
Yeah.
How hard can it be to compute a determinant? Sounds like a good question to me. Has somebody done something like this? This guy, yeah.
No.
We actually had some.
No, but he never cared about this,
yeah.
Greg. He only considered this enormous perspective.
Pandas.
No.
Pandas.
No. People never consider this near horizon setup with this graviton hairs outside.
Too hard. Sounds like a good problem.
Okay, given that, let us go to the main part of today's talk. So I'm gonna talk about QFT duals of AdS black holes. So as you know, black holes are fundamental objects in gravity described by smooth geometry as event horizon, but it has been known that they encapsulate high energy state in discrete spectrum of quantum gravity. So today's goal is to statistically account for the Bekenstein-Hawking entropy of black holes through hologram. So you have entropy proportional to the horizon area, and I want to interpret it as the degeneracy inside the horizon. So this kind of approach, at least qualitatively suggested from long ago. So you have Hawking phase condition in AdS gravity. At low temperature, you have thermal gas of gravitons, but in high temperature, you have stretch of black holes. And in the dual gauge theory, they correspond to low temperature confined phase and high temperature deconfined phase. So our goal will be to find deconfined phase from the position function of the dual gauge theory. So we want to study strongly coupled gauge theory. And in order to do so, we will focus on the BPS sector set in which certain operators are protected, do not receive anomalous dimensions as strong coupling. And we will consider large AND gauge theory to holographically study the semi-collectible black holes. So our observer is the so-called superconformal index, which long ago produced by Shiraz and his collaborators here. This is nothing but you can think of it as Witten index times server partition function on S3. So you have -1 to the F here and introduce various chemical potentials conjugate to arbitrary descent angular momentum to ensure that this exponent is commute with our chosen supercharge. And this index will count the BPS operators analyzed by our chosen supercharge with -1 to the F. And by definition, it is protected under any continuous deformation. So you can compute this quantity exactly at weak coupling to study strong coupling dynamics. So for a moment, let us only find all the chemical potentials like this. So you have only one QST X. And you can consider some expansion about X, and this will give you the degeneracy at each charge sector. And this unrefined index has unitary matrix interval representation given as this. So this vector comes from the single bit tessellator I already shown to you, this scalar, spiral, and things. So their contribution to the index. So this denominator comes from the holomorphic derivative. Arbitrary number of holomorphic derivative can act on them, and this numerator comes from the scalars, parallel scalars, and so on. And they are all in the adjoint representation of the gauge group. And since you do the plasticity exponentiation to get the multi-particle partition function, and finally you do the Hamilton integral to extract only the gauge invariant of contribution from the gauge invariant.
And very sorry. So for some reason, the e to the minus delta I is set equal to x square, and this is for some computational.
Just for computation.
Otherwise, there's a more general.
Sure.
It's a more general formula, but still there's one part of physics. Suppose you want to count, you don't want to distinguish between the three SO6 stars. So we're setting all those in the potential. And you don't want to distinguish between the two angular. We're setting those. That is a computational convenience. But now that these two chemical potentials have to be
they should be related.
That is because it's an index. It's only an index and that.
Yeah. Because you want to make it commute with supercharge. So yeah, there is one relation between the chemical.
So this is one example of this general thing that indices are not codimension, are not 5-parameter.
Yeah.
They're 4-parameter. So that he's gone from 4 to 1 is convenience. But from 5 to, in that space where all three charges were equal and all two chemical angular momenta are equal, you might have thought there were two chemical potentials. But 2 to 1 is not convenience. It's forced on you by the
This is the commute with supercharge. And so what I want to see is let's say this is just normal contour integral. You can compute using residue theorem using the computer up to reasonably high orders in X and reasonably large n squared and expanding in X. Okay, so using computer you can compute quite well. So let's say in U5 we compute until x to the 100, and U6 we compute until x to the 70. And you can see this number is quite large, right? So the degeneracy is macroscopically large at large J and large N square. But the thing is that the sign in front of each degeneracy is rapidly oscillating.
This is the free theory, is it?
No. So
somewhere,
we compute that recoupling, but since this is the index, so it is protected quantity. So you can view it as strong coupling then.
But because there's sometimes a story that the exact free limit is a bit special. You want to, so I'm just asking. You come to it maybe.
Non-zero finite coupling.
Non-zero finite.
This Hamilton integral is the effect of that.
Yeah. So the only effect of interactions is to impose that things are Gaussian.
Yeah, Gauss law.
That's the only effect of it. And the reason that it's not more special is that we're on a sphere. Because we're in a sphere and all the scalars have conformal coupling, the theory is massive.
Yeah.
So it's not like there's a mass, it's a very clean system.
Yeah, Gauss law, of course, you'll have to impose.
You have to impose.
Yeah.
You might have just made it a quadratic integral. From the point of view of the path integral, Gauss law is not quadratic because it's A0 phi bar phi. So if you were naive and you made it just really a quadratic path integral, you'd miss the Gauss. So we have to impose that Gauss law. But apart from that, there's no other interaction.
Everything, all letters are gapped.
Everything is gapped. So it's a very clean system.
Yeah. Okay, so we compute this, and we draw this in this figure. And this black line is nothing but the black hole entropy, just putting n equal 5 or n equal 6. So you can see that the index degeneracy really agrees well with the black hole entropy, a large J. But the thing happening in here, the blue and red dots means that the sign in front of the degeneracy is plus, minus, plus, minus, plus, minus. So the entropy, the degeneracy of this value is the entropy, but on top of that, you have rapid sign oscillation between the boson and fermion. And the question is whether can we account for this kind of behavior from the index, subpoint approximation of the index.
When you draw this line, you are drawing it for the black hole whose charges correspond to where the index line penetrates this black sheet. Right?
Yeah. I've been saying charges like this.
Sorry, what is J was the equal angular momentum and omega was the equal upcharge. Okay.
J is here and omega is degeneracy. Degeneracy at charge.
Sorry.
Yeah.
Okay.
Sunjin,
Yeah.
so why are these positive and negative coefficients coming clumps?
That I want to explain now. That is a very important observation here. So this means something. So can we account for this from the self-point approximation? So the Legendre transformation from the free energy to the entropy is nothing but the self-point approximation of the inverse Laplace transformation. So yeah.
Want to see the region of the charges where there is no black hole. Where should you want?
You mean very small charge?
Yeah, I was wondering where there is a black hole doesn't exist for all charges. Right?
Here. So charge is very small. So this is actually this actually agree with the gravity conditions.
But I think you're talking about where the black hole sheet is finite and the lines miss it, right?
You're talking about that. That cannot be seen from the index. So we have index line, and index line always cross the black hole sheet.
Not always. I mean, he's because you said charge. You're looking at Gutowski real. That's true. But he's saying look at more asymmetric charges. Then you can.
One could do the different areas.
But
Then you can see that.
yeah, but in this setup they always.
So in this,
Yeah, in this is only fine. So.
Yeah.
Okay, so this omega j, when charge is very large, you can do the inverse. So basically, you can extract omega j from the index by following inverse Laplace transformation, and the self-point approximation of this integral L large charge is nothing but this Legendre transformation. And if we are computing normal partition function, computing the bosonic plus fermion degeneracy, you will find a cell point at real omega for real charge. But since we are now computing the index, what I want to argue is that you should find complex cell points at real j, complex omega at real j, and which means that this leads to the complex entropy. However, our unitary quantum field theory always have complex conjugate pair of such cell, and meaning that if you add these two equally dominant contributions from conjugate pairs, you'll have exponentially growing envelope function times oscillating factor between +1 and -1. And the full entropy will be given by this term plus log of cosine term. And this cosine is the reason why you have always this kind of bump.
Okay, on that plot, can I ask you, just if you can go to the previous slide?
Yeah.
Please? Yeah. So as far in the black hole limit, the transition from Hawking page to black hole will occur at charges of order n squared, right? I mean, energies of. I'm just asking.
Yeah.
So isn't it shocking that at n equals 5 you get such a good match?
N equals 5, then n
Is that
equals
what you have U5?
yeah, but n
I
equals
would have expected, you're way off or something.
yeah, but n equals 5 means that n square is 25,
Okay.
which means it will be large.
It's like remarkable.
Yeah, of course.
Initially.
Yeah.
Okay.
Now, why aren't the gravitons comparable? You're asking, right?
Yeah.
At those charges, you could compute what the gravitons would be.
Yeah,
And check how big they are compared to this.
yeah. Actually, at this,
compute in supergravity for the black hole, you can compute the gravitons. And presumably you'll find that's a very small contribution.
Actually, at very small charges, these are where is the gravity.
Just for more, the crudest way, just count traces.
Okay,
Count all traces that contribute at this charge.
I see.
Right? We could count that and we get some answer. He got very big numbers, right? I mean, these things, because he's plotting a log, it doesn't look.
Yeah,
But his
actually, it's
numbers
very large number. Yeah, even from U5, you have very large number. Hence the 16 like this.
So somehow.
So e to the power n square, even when n is 5, it's pretty large number.
Very much. It's comparable to 10 to 16.
Yeah, but it is totally crazy.
Yeah.
That's why.
So, as said, for the index, which represents oscillating signs, unlike this normal partition function, even at the real charge, you should find complex conjugate pair of the cell point for the chemical potential, and adding them, you'll have exponentially growing envelope function and times oscillating factor between +1 and -1. So this is the reason why we have this kind of bump behavior: boson dominate, fermion dominate, boson dominate, fermion dominate. And this first factor is the leading term, and it gives the macroscopic degeneracy at large J. And this will account for the vacuum channel entropy of the black holes.
Sorry, I mean, this suggests that there's a one of the oscillations. Right?
Yeah.
But why boson dominate?
Sorry.
Why is it that bosons dominate the fermion dominate? You're saying, oh, because this is cosine.
Cosine factor. Yeah.
Sorry, what is the meaning of this imaginary part of entropy?
Well,
What does it represent in that plot?
well, this is typically subleading because you have log of cosine. So, but this, well, first of all, this tells you whether at each charge the entropy comes from boson and fermion, and secondly, it'll give you some subleading contribution to the
Sorry,
entropy.
if you go back to the previous slide, how does that is the clump that is happening for, let's say, some omega j, the clump that is happening, how does it change if you increase n, capital N?
Well,
Will the clump increase? Like the
yeah,
size of the clump?
you can see that this is a bit larger than this.
Sorry, this is for n equal to 4. Sorry.
U6 and U5. Yeah.
So it will keep on getting increased, bigger and bigger. Is that so at very large n, at very large n, all the states will be bosonic. Is that?
No, I mean there will be region where boson is dominant and then fermion is dominant and so on. So this bump is the width of the bump is, well, it seems that it's proportional to n, but we are on the Blackwell charge is usually proportional to the n square. So compared to the Blackwell charges, it is very small region.
Okay. So I thought that's roughly the imaginary part of the chemical potential to give you that frequency.
Yeah.
And wasn't that independent of element, the large element? Or is that wrong way of thinking?
At this point, it doesn't seem so. It looks it depends on, and also actually it depends on also charge.
Yeah, it depends on charge.
Yeah.
But maybe that's why it's depending. Because it's depending on Q by n squared.
Yeah.
But right. But if I do the fixed chemical potential, then that will stay fixed in the large element. Because it should be governed by roughly the imaginary part of the chemical.
Yeah, that's true. Yeah, that's true.
Fine. Got it.
And if you go to very large charge, this will become larger and larger.
Yeah,
So
if I do it fixed Q by n squared,
Yeah.
Doesn't that suggest that microscopically you can take one particular value of B or F? Because it's that thing is at least staying order 1 in the margin, right? It's not.
Yeah,
going
yeah,
by
yeah,
one
yeah,
over
yeah,
S5.
yeah, yeah, yeah. You can stay on from region where boson is dominant or fermion is dominant and so on.
But it also, there are places where, of course, you won't actually see it because it's not fine grained enough, but it also goes to zero sometimes. This is cosine. It's going to be interesting, right?
Yeah. That's a very interesting point. Although in this numerical study, we couldn't find precisely zero, but if that happens, that will be very
What does
interesting
it
point.
mean? What does it mean?
That's very interesting.
Cosine is coming in the log, right?
Yeah.
So
Cosine is coming in the log because you're taking something and writing it as e to the bus.
Yeah,
Just like the degeneracy. That has a cosine answer.
in degeneracy, you have just cosine, so well, in principle, it can be precisely zero, but yeah, that's very.
It means the whatever the entropy or the number of states
Vanishes.
I think getting zero is like probably the getting zero.
Very small.
Yeah, very small.
Equation is-
Very small, but yeah, we
As
don't
you
know.
go over these things, there will be things that come nearer and nearer to that. Because there are many of these ones.
I mean, that's log plot. So like, if you really want something to be zero.
No, but let's say I give you a fault tolerance.
Yeah.
Epsilon.
Yeah.
I see. But you're saying even epsilon being n's, if I take epsilon being some power of n,
Yeah, that's like
very
very
unlikely.
unlikely.
But still, even if it's small compared to 1.
Yeah.
But you're saying because it's the log. Okay, maybe not. Maybe it's hard.
Yeah, it's true that it is very unlikely. Unlikely
Isn't
happen,
it
but
order 1? I mean, that epsilon tolerance doesn't scale with n, right? Even expressed in terms of chemical.
Yeah, and then I think Ungu's point is that the number of states is epsilon times e to the power n square.
Oh, I see.
And so if epsilon is some 0.1 by a million, who cares? Because that's e to the power n square. Right. Yeah. It's somehow still, it's very striking phenomenon. And yeah.
It's that bosons and fermions are about equal. Right? Is that a
I guess it's they assume similar or ETN square plus.
Yeah, as Sandeep says, because if we take the cohomology, so we take the zero temperature limit of Lorentzian black holes, not these funny Euclidean black holes with complex stuff, then we shouldn't expect oscillations because chemical potentials are real. So somehow this is this is something presumably of the index that will not be in the cohomology. Do you agree?
Sorry.
Do you agree that these oscillations
Mm-hmm.
will not be there in the cohomology? Suppose you computed the cohomology without the -1 area.
Mm.
However, we don't. Would you expect these same oscillations? It seems to me that this is an index versus cohomology. And then that goes towards Sandeep's bosons and fermions and yes. But I don't know if it's true. Is that a way to make this percent?
Yeah, I don't know. Yeah.
Yes, so that's a much more intelligent reinterpretation.
Okay, so yeah, as I said, the sines and subleving oscillations using this cosine function very well match now. And this justifies our interpretation of complex cell points of the Legendre transformation should account for this sines and subleving oscillations of omega j.
The cell point that you're talking about is the cell point of the
Legendre transformation. Legendre.
so how do you know the integrand? You just know you can see this one.
You mean z?
Yeah.
For z, we just here use the black line property function. So we are comparing our numerically computed index with the black line. And this we use the black one challenge. You can see now that this our cosine interpretation and numerically computed index quite actually well. So from this lesson, we learned that in order to extract this macroscopic degeneracy from index, which sign oscillate rapidly, you have to find complex cell points. So keeping in mind that we now consider the index and finding complex cell point of the index. So now we deal with all refined chemical potentials. So now we have 4 chemical potentials because we are dealing with the index. So they are constrained by these. So yeah, for convenience, I absorb -1 to the F to the definition of chemical potential. So apparently there is no -1 to the F, but because of this constraint, they come up with supercharges and it defines the index. So this index admits unitary matrix integral as before. And the different thing is that now the singulatory index is refined as this. So you have holomorphic derivative contribution from the holomorphic derivative, and this is coming from the singulators, the scalar elements, and so on. And we would like to find saddle points for this matrix, index matrix model in the Cardi or original limit goes to BPS black holes in AdS5 times S5. Yeah, this is our formula. So for simplicity, let us first consider the Cardi limit, where this omega is very, very small. So omega approaches to 0, in which the angular momenta, the conjugate angular momenta, will be very large. And after some computation, you'll find that this exponent can be greatly simplified as this, using this trail logarithm function. So basically, omega, when omega is very small, you can expand this. So in the denominator, you will have omega 1, omega 2, and you will find n cube in the denominator, which will give you Li3.
Why is it called a Cardi limit? I mean, this is not
Yeah. Well, in the in the 2D CFT, you have you call the Cardi limit as this.
Say 0 or infinity, one of the other.
Yeah, the chemical tau goes to 0 limit, and then the angular momentum become very large, right? So this is analogous to that limit, so we call it just Cardi limit, in which the angular momentum become very large. Yeah, and this pair can be also greatly simplified to the polynomial. This is Bernoulli polynomial. This is just nothing but a cubic polynomial. So we have cubic polynomial of these chemical potentials, and because we only have this adjoint fields, you can find that so-called maximally deconfining cell point dominates this integral. So that this eigenvalue assume all the same values.
I'm getting confused about your X and omega. What is X?
Where is X?
V3 of X.
Here X. This is the identity.
Okay. So that is whatever's inside these NIs.
Yeah. X. Yeah. Here our X is this.
Okay. X is neither big nor small. It's just something. Some order one now.
Yeah. It's just identity.
And so even though it's neither big nor small, it's just you're not doing a small X expansion, but you find just a terminating point.
Yeah. It's just cubic point. All the approximation we use is omega is very small, and this is already expected on.
Quick question. There was this. Sorry, no, it's a bit tangent. There was this old paper by Komar-Gotsky, Pietro, whatever that one where he tried to apply this thermal partition function method to indices. And from that point of view, you would get a derivative expansion in this e to the power x. Do you understand why it terminates a third?
Why? What?
Why it terminates?
Terminates.
Why? Yes, you're saying basically that this thing is just polynomial, right? And then it's cubic order. So it feels like from that point of view, that terms with higher and higher order derivatives don't contribute. So wondering if there's a supersymmetry reason.
Oh wow! Oh, sorry. Okay. So that is because we only consider the leading term. Of course, you can have some one. This is 1 over omega square, but you can have 1 over omega to the 0.
No, but just let's take the leading order term in small omega, but arbitrary powers of x.
He just asking this idea. This Li3, very complicated stuff. but at the right hand side, it's terminated.
Just a comment, something very similar to this happens for free scalar fields in 4 dimensions.
Yeah.
Very similar, except that in addition to this terminating polynomial, there's a whole instanton sum, an infinite instanton sum. I mean, e to the power minus 1 by, I suppose it would be minus 1 by beta, that minus 1 by x, I think. So it's and in this paper we're putting out now, we have a long song and dance about these instantons which are absent. Okay. Sorry, please go ahead. I'll talk.
So you can understand this from modular transformation of this. Sorry, what from the modular transformation of the land of that is omega going to zero limit, that the other product factors once.
So you can organize this as the elliptic gamma function and do S transformation, and you'll find that this S transformation elliptic gamma function just only give you the non-perturbative suppressed part, and you have E to D some leading part, and that is this.
And the other part just goes to
One.
So one last comment about this. One could take this partition function, this is S1 times S3 partition function, and do a Kaluza, like we did 15 years ago, right? Do a Kaluza-Klein reduction of this.
On S3.
On S1.
On S1.
Okay, so you get a bunch of fields on S3. Now, because you've got this omega very small, I presume these fields are like very massive.
Yeah.
So now we can do this path integral of these very massive fields accurately in a world line kind of representation.
Yeah, on S3 you can do I mean that approach already
Has been done.
Yeah.
And from that point of view, you understand why that's a terminating polynomial.
Okay. Yeah, in that approach, we just wrote down every term you can write in effective Fuller theory, and you will find Charles-Lyman's term dominates in this cardinal limit, which is dictated by anomalies. Maybe anomalies are finite polynomial. So it terminates.
Yeah, I was wondering if the number of supersymmetric terms you can write is finite.
Yeah,
fine. Or that it's just you could have written more, but
no.
If this expression like you're doing some approximation when you go to zero.
Yeah. I mean, in the leading order up to this order, you can only write finite terms.
No, let's look at just an exact expression for the coefficient of 1 by omega 1. There are other factors than omega. That's why. Oh, you're saying anomalies should be why do anomalies? Yeah, okay, I know. Interesting.
And in this order, only anomaly polynomials can contribute to this effective Fuller approach, and it's better actually.
Because apart from the usually in this fluid dynamical picture, anomalies dictate some low derivative terms. But higher derivative terms you cannot control.
Yeah, that's true. But this is the index, and somehow the order is reversed, and this anomaly term dominates.
Okay.
Another way of asking this perhaps. So when you do this modular transform, when you have the additional factors, I remember that you get these elliptic gamma functions where parameters, sometimes called sigma tau, or in this case omega 1, they get to 1 over omega 1 and omega 2 by omega 1. Right? But when they go to 0, the first goes to infinity. One of them goes to infinity, but the other you go to 1. Right? So I'm just trying to see how can the whole thing go to 1. This is a bit technical question.
Yeah, so you have two modular parameters, right? And you have double expansion, but apart from, let's say, one term, I think all the terms always have both vivasties. So if you have the modular parameter going to 0, then it will be just gone.
Because one of the modular parameter after the modular transform is 1 divided by omega.
So that cannot give you the suppression factor, but the other modular parameter is 1 over omega 1 give you the suppression factor for all these double expansion forms. So they vanish. So we have this simple integral in the cardinal limit, and in this cardinal limit, you will find that this simple settle point will dominate the integral. And actually, this is what we want. So at very high temperature, all n square matrix of degrees, all n square matrix degrees of freedom is liberated, meaning that they deconfine. So this is really the deconfined quantum plasma. And
How do you see that that's the saddle point? You explicitly compute it?
Yeah, I mean, basically, you all the fields are adjoint fields. So because of the symmetry, you can easily confirm that this is the cell point.
And that's the saddle point which dominates. So,
Yeah, that it
because there is no
dominates.
phase cancellation is something as simple.
So what kind
I
of?
mean, these phases alpha A minus alpha B.
Yeah.
If you set them all equal, they,
Yeah,
they
yeah.
will all add up instead of oscillating around. Is it
Yeah.
as simple as that? or-
Yeah. Right. You're right.
In our old paper, we had argued that this will never happen because there's one that comes from pushing away the
You mean how much?
R measure, and then there is this f of x. And when we stuck to real chemical potential, that f of x was always less than 1. Always the repulsion beat the attraction. Here, from this point of view, it's like that f of x goes larger than 1 and goes very large.
Yeah.
So now this attraction way beats the repulsion. So all the eigenvalues stick together. Basically just.
Because we are in a complex chemical potential, this can be very large in some region, and that attraction is much larger than the Hermitian pressure.
I'm very sorry, please. Not quite getting the Lorentzian case clearly corresponds to real chemical potentials. What is this complex thing? You do a Euclidean problem. Is it an auxiliary problem or sorry? Why?
Well, in the purely field theory side, we are computing the index,
So therefore, I understand the -1 to the f. Oh, but the index is defined with these extra phase factors. Is it?
So
Yeah,
you can introduce complex chemical potential.
Yeah, so yeah, you can. That's clearly okay.
It's very confusing, right? This is the thing we got wrong right here. We had assumed real charges will get real chemicals. The point that these guys make very effectively is that this -1 to the f can anyway be thought of as an imaginary chemical potential, let's say for J. So that's already some source of this imaginary. And now you can ask, can you get real charges? The charges have to be real. Can you get real charges with some more interesting complex chemicals? And you can. This was a key observation.
Yes, and that is the role of, the role of complex chemical potential is, as I said, making this simultaneous. And so you took this cell point.
But so far there's no assumption about X being complex here, right? So when you say that.
So we take the limit in which omega-1 and omega-2 goes to 0, meaning that they should have real imaginary. So everything is. So yeah.
So the saddle doesn't depend kind of sensitively on the, let's say, real part, imaginary part.
No, because we are considering these limits. But if you slowly increase the omega, of course, they will depend on. But this leading order, they just have the same number. And if you put this cell point on the integrand, you will get a low z as this is the Cartesian energy. And yeah, actually, this function has been suggested as the entropy function of this black holes in AdS5, meaning that you Legendre transform this function, then you will get the Bekenstein entropy of the black hole.
This is not, deltas are not real, right?
Complex.
So this product is real.
No, complex.
Okay, I see.
But the charges will be.
The charges will
be.
So you
So
Legendre transform and real charges.
Okay.
And as said, you will find complex conjugate pair of the chemical potentials, and adding them, you will have a real degeneracy.
Thank you. Thanks.
Yeah. And now one can ask that. Yeah, so
let's know. I was just saying is that always you should think of all this canonical stuff as an auxiliary. Always the real question is what is the entropy as a function of charge?
Yeah.
Just think of this as mathematics.
Yeah, this complex phase is to because of we are computing the index and because to imitate the sign oscillation, that is why we produce this complex phase. The final answer can be real, because real charge, real digital sense. So yeah, we studied the simple limit, and this will be due to very, very large black holes in bulk. And we want to ask whether can we also account for arbitrary size of black holes. That doesn't discard limit. Let us.
Very large just because it's the deconfined.
No.
Very large, sorry.
In this the angle momentum is very large. This is 1/omega cube or something like that. So parametrically large. Of course, they are all charges are all n square, but they are parametrically large. But now we want to go to beyond Carnot limit. So as omega becomes larger, as Shiraz said, the high-measure recursion becomes important, and these eigenvalues will be spread. Roughly, the width will be order of omega. And we, nice question can we find cell points at finite omega, only assuming the large n length, which will be just dual to arbitrary size biggest black holes needed by AdS5. And the matrix integral can be written as Abhijit said, the product of elliptic gamma function. This is just another way of writing same integrand, and this elliptic gamma function is this double expansion form. And well, for some reason we redefine the chemical potential in this language. Somehow using this elliptic gamma function is better to use this variable, how sigma and small thing.
And sorry, just you're working at essentially 0 to coupling up to those. Is that correct? Just in the
Yeah.
Got it. Okay.
And we want to compute. We want to find large and saddle points of this integrand utilizing some SL3D modular properties of this elliptic gamma. And before going that, I will first illustrate some simple point model. So let us consider some partition function given as some potential with tau periodic two-body holographic potential. So meaning that U plus tau equal to U. And obviously the knife saddle point will be just uniform density along the top. This is just periodic direction. So you just put the eigenvalues with equal distance on the circle, right? This will solve the saddle point definition. If you have tau periodic potentials, meaning that you are working on the circle, effectively circle. So the knife saddle point will be just put the eigenvalues with same distance on the circle. We have all.
Depends on what B is and so.
Sorry.
It depends on what B is.
Yeah. So I'm illustrating some toy model. Yeah. Suppose that we have this kind of potential, and the saddle point will be given.
And U is like, it's like a difference between positions, right?
Yeah, two-body potential.
Two-body potential.
Yeah.
Then it's clear because it's isometric. I was thinking that if you've got just two-body potentials and you have a uniform distribution on a periodic direction, then that will solve it.
Yeah.
Because which way will the force work?
Yeah.
Will it work that way or that way? It's balanced fairly.
It's also holomorphic. This was a distance, right?
Yeah, we are working on all the complex variables, so the V should be holomorphic.
But that is some e to the complex stuff, then, right?
E to the complex, yes.
Then how do you do saddle point with this complex?
Well, the saddle point equation is nothing but okay. So force on this eigenvalue will nothing but the derivative of potential and integrate for all the other eigenvalues, and because of this periodicity of view.
If it's a very attractive potential, why won't all of them clump together?
No.
Term or anything here.
No, we have reflected.
So what is in matrix integrals, of course, you get a repulsive term from the measurement over here. I thought this is all you're doing, right?
Yeah, I didn't say, but
Oh,
it should be
okay.
the repulsive.
Oh, there's a, okay, then I understand. Oh, very, very good. Okay, thank you.
Basically, the Harmaser term will be the
Okay,
repulsive.
so then of course you have the can't sit on top and then it's reasonable. Okay, now I
What will attractive and repulsive make sense when something is real, right? Potentially is real.
Uh-huh.
This is V is supposed to be a holomorphic function of UAV. So what is this repulsive attractive or nature?
Yeah, basically, yeah, you're right. That depends on the direction, but
You can't have log of Zi minus Zj power, so at least it doesn't like, I don't know.
they always
Much energy.
measure. They always give repulsive potential. I mean, that is basically log of Zi over Zj. So if you put them in the same position, it will cause infinite energy. So they want to repulsive.
Okay, but that is that. Okay. Yeah, this seems to be a too fast argument. Well, I know where you're going with this, right? The next study, but that is somewhat of a non-trivial conclusion that I wanted to understand.
But the thing is,
based on
here the thing is that even if you don't think it is repulsive, because of the symmetry, it is really the local setting.
Yeah, it may not be the best center.
I'm not talking about the global, but local
Just
setting.
algebraically, we could probably,
Yeah.
holomorphic or not, show that the forces cancel.
Yeah.
Just because each guy has a partner on the other side. That will just cancel the forces.
Yeah, it will be always the local stuff.
yeah.
So
Yeah, that this is a saddle is probably clear, but there may be other saddles that more down.
yeah, that can happen. Yeah. So the next question will be: so as I show this figure, are there any non-periodic periodicities like this hidden inside our problem? And the answer is yes. So you do the S transformation.
Could you go 2 slides back once? Say a little bit more about what this gamma is.
This is the so-called elliptic gamma function, and this is just funny way of rewriting the integral.
So it's just the integral.
Yeah.
Okay, it's not. Okay, so now, but you're now going to tell us that it has some nice properties that are not obvious. Okay, fine.
Basically,
Abhijit knows all about the.
yeah, you should.
So just to see, I mean, this elliptic gamma function, basically the derivatives are some derivatives give rise to. I mean, if you just so this exponential structure is gone. It's written as you would write for a boson. X goes to 1 over 1 minus x, the multiparticle, right?
Yes.
But if you now have a derivatives acting on that, then it would be 1 over 1 minus x times 1 over 1 minus x cube, and 1 over 1 minus x cube square, blah, 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 right?
Yes.
So that gives you infinite product.
Yes.
In the denominator, but that's one derivative. If you have 2 derivatives, the p tower and the q tower.
Yeah.
So roughly that is what is being encoded in this graph.
So in 2D you have
it's a double.
in 2D you have Jacobi zeta function, right? And in 4D, since you have 2 derivatives and it is generalized to elliptic gamma.
So the denominator is the various derivatives. Yes.
No, both of them. So denominator was only the numerator is fermionic, but you n comes from the arbitrary number of derivatives acting on them.
The tower is from the derivative.
Yeah.
But why do derivatives show up in the I see.
Fermions.
Yes.
Fermions also get down.
I see.
They both separate.
So just like the SL2G modular properties of Jacobi zeta function we saw in 2D CFTs, this elliptic gamma function for the gauge theories enjoys some SL3Z modular properties, and in this SL3Z modular properties you can find some analogous to this SL2Z case, analogous S transformation. And so if you transform this gamma function, you'll have 2 factor of gamma. On top of that, you have this anomalous factor, just like the 2D Jacobi zeta function, and you can see that quite similar to the 2D case. You have 1 over tau and 1 over sigma. And the nice thing is that, and also it enjoys some T transformation. or I don't know. Let me say it has periodicity. So if you what can I say? Gamma z plus 1 is gamma z. So if you have this factorized integral, this factorized part will enjoy the periodicity separately. If you translate z to z plus tau, then it will be periodic, and this will periodic under shift of sigma. So this S transformed integrand of our integral can be written as this, and this V sigma coming from this vector, this vector is periodic under the sigma shift, and this V tau will be periodic under the tau shift.
So sigma, tau, and z. Z was the holonomies?
Yeah, that is the whole
Sigma is what and tau.
sigma tau are the omega 1 and omega 2 divided by minus.
The two and one.
Yeah.
Okay. So the two sort of five circle directions.
Yeah.
If you think of S3 as embedded in R4, these are the two circles, right? Okay. So you've got some sort of modularity between the two circles on the S3 and the holonomy. So the holonomy I should think of as being coming from the S1 circle. So the two circles on the S3 and the S1, in the S3 times S1, these three are mixing. Amazing.
Yeah, this I try to explain it.
In your paper, yeah. Can you 1 minute give a review?
Sure. So,
Very sorry. So just prior, just to why are the two circles on S3 you make embedded in S4, and then you have two rotations R4, and then you have two rotations which come in.
It's
how
two
it
fields.
right? Okay, please go. Yeah.
so I mean, one way of understanding this S3 times S1 just to begin with. So is by understanding S3 as a gluing of two solid total. Right?
Yeah, like within does.
Like within does. So all the same this topological difference can be made sense of in terms of geometry also. So then S3 times S1 will be understood as gluing of two solid three total. And then when you glue that, you would have to specify how you are gluing it. So there is a large diffeomorphism of T3 that it does.
Yes.
That large diffeomorphism T3 is SL3's basically.
Yeah.
And then there is also a place for the shift symmetries, which is an automorph, it's got some product with the ZQ, which is like a shift symmetry, so that can be avoided. So it is not the usual type of modular property that we have with the theta function, where it just says that you have a torus, you just swap your point of view, time and space, you get the same thing. And that's why the partition function should roughly be the same thing up to various anomalies, right?
Yeah.
But that's not what is being said here. The modular transfer is not as simple, right? It's not saying that you do this kind of thing, z going to z by tau and so on, then you get the same thing. But rather this gamma gives you product of two gammas up to this extra factor, which is roughly that the extra factor is the Jacobi theta function into dimension.
Yeah.
So that complicated thing comes from the fact that it's not the usual modular property, but it's a modular property of the pieces. And then pieces need to be glued.
And sorry, the S1 of the S3 times S1 was at all on the same footing as the other two.
It's clear.
Wow, that's right.
So they have S3 times S1. You just forget that S1 for a minute.
Yeah.
You just look at S3. Now that's a two torus, solid two torus glued to solid two torus. Now let's look at only one half of that, which is a solid two torus. The two circles that you talked about in R4 are the two circles on this solid two torus. Right? And then you are tensoring it with the circle that I had ignored.
Yes.
So finally, what did you get? A two solid torus tensored with a circle. But that is also a solid three torus.
Yeah.
So once you have solid three torus, the boundary of that is three torus, and all the circles are the same.
I see.
Thank you for the detailed explanation of this the gamma. And with these modular properties, we end up with two factorized.
So you think of this like you cut it and you get a wave function.
Yes.
And then the final partition function is an inner product of two wave functions.
Yeah, sure.
I see.
We don't have anomaly issues, but this can be understood.
Yeah.
So since we have two factorized periodic potentials, as we learned from this easy example. So one can immediately imagine that. Yeah.
And is this Hilbert space in which this wave function lies, is that finite dimensional Hilbert space? And that is
for n equals 4 for finite, yes, it is. You can do a localization now only on half of the geometry. And it localizes to what is called the Higgs branch vacuum. So this is you basically consider massive theory in this solid three torus, and people have done this localization which are finite dimensional. It's like if you have a QCD theory, there is some combinatorial and C choose and NF choose and C, that kind of thing.
Okay.
Number of vacuum, the number of vacuum that it will go.
And you use this finite dimensionality to say something.
Yeah.
So you say that whatever this is in some
this modular basis. So in this case, in the free theory, because he's looking at the transformation of the integrand, right? So that's the free theory. So there is only one dimension. It's only one dimension. In gauge theories, right? This is the sum over things like that. Sum over this elliptic output. The final integral, right? But then each summand is understood as coming from one particular vacuum. And that is running through. And each project, if you project on that subspace, each of them will have this problem.
Nice. And to explain his relations, gamma, then you're using just a one-dimensional Hilbert space.
Yes, one dimension.
So then this is as easy as Beaton.
Yeah.
Right. Okay, fine. Okay, thank you.
So we have two factorized periodic potentials in sigma direction and tau direction. So the naive saddle point one can guess is that just consider a doubly periodic saddle point, which is periodic in the tau direction and also periodic on the sigma direction. And this will obviously be the saddle point of these two periodic potentials, right? So we have this uniform parallelogram distribution, as we can suggest this uniform parallelogram distribution as a saddle point. But it looks a bit weird because we haven't seen this kind of areal distribution from the unitary matrix model, right? So there will be some subtle problem to realize this at a saddle point. So what's wrong?
Before you did some transformation on the integrand.
Yeah.
You wrote that as two gammas.
Yeah.
Why did you have to do that? Why not in the original?
You could, I think, just to realize that there is symmetry.
Yeah, in order to see this symmetry in your bare eyes. Yeah, in your bare eye. Yeah. So what's wrong about this saddle point? So our potentials are made of logarithm of elliptic gamma function, meaning that it'll have many branch points. And if some branch point or log is inside of our parallelogram region, then it will ruin our periodicity argument, basically, because if you integral over circling this branch point, it will not give you 0. This is not periodic. You will have 2 pi length, right? So this will make our statement wrong. And this really do happen, and the answer is yes, because you can easily confirm that in our integrand, you will have R measure, and this term always give you the branch point inside our parallelogram saddle point, which means that our naive guess is wrong. But so our naive guess is wrong, then so what about the naive guess? Naive guess is that the parallelogram distribution will solve the problem.
Uniform distribution.
Yeah, parallelogram uniform distribution will solve the problem because of the periodicity, but because of the branch point, which break periodicity in a very subtle way, this will not be the true saddle point of our problem. And the next thing we considered is that, so we have some nice answer, which is not the answer to our original question. So we deform the question to make our answer be right. So our integrand has this form. So this is the R measure, and there is a identity which makes this integrand into the different form. Basically, you discard half of the half measure. And these two integrand are different, but by mathematical identity, the integral of these two functions are the same.
While invariant functions.
Yeah, for the invariant function. And our integrand, of course, is invariant. Yes, that is part of case. And here, if after using this integrand, you can order the eigenvalues so that this vector is always smaller than 1, meaning that in our region, there is no branch point. So no branch point coming from the half measure, this term. And for the other term, we have plenty of vectors, right, from the chiral multiplet and so on. And you consider all the branch points coming from other metric contributions, and you can confirm that their branch point can be evaded in this restricted domain of chemical potentials. So if we assume this inequality between the chemical potentials, all the branch points of the integrand can be put outside of our parallelogram region. So under this constraint, our parallelogram and such work well, and it is the Lorentz saddle point. So with this saddle point, we compute the Lorentz free energy and have this form, and you do the Legendre transform onto the real charges, as said, and you will find, yeah.
When you say that now you take the saddle and compute with the energy,
Yeah.
There was a similar factor already there from the B, right? That is it that now this, when you say that you compute, this is just 0 and you get that. So after doing like this, the action just 0.
Yeah, basically this is periodic function. So you put all of this periodic distribution, they just vanishes and you have all
That's
this.
the big answer.
Yeah. So you got this function, and this is the entropy function of the black hole. So basically, you do the Legendre transform onto the real charges, and you will get this kind of entropy. And this is nothing but the entropy of the vector booking entropy of the black holes in AdS5 times S5.
But sorry, I thought you were computing an index, but it agreed with the full Bekenstein booking.
Yeah.
And then what's the explanation for that here? I mean, just to ask. So it seems like only that there are no cancellations again somehow.
At least at leading order.
At least at the leading order. Yeah, so we have.
So really you're landing on completely boson.
Yeah, we have e to the n square number of boson and e to the n square number of fermion. But if you subtract them, if you have small difference between boson and fermion degeneracy, just one will dominate. E to the n square is very large. So this cancellation structure cannot be seen in the leading.
So, and can one conclude that it's the bosons that are dominating because you didn't get minus the.
No.
Right? So you're not sensitive to that.
Yeah, I mean, as
in entropy, it's a I or something.
Yeah. I mean, this entropy should oscillate between boson and fermion as charge changes, as I said. Already.
Yeah, there's an imaginary part to this as well, right?
I didn't show that.
There is an imaginary.
Yeah, imaginary part will oscillate between boson and fermion, as I saw. As shown.
So you had some validity condition for your analysis.
Yeah.
So when that validity condition goes wrong, do you see something? Do you see some, as you approach that, do you see some problem with this? Or?
So in computation, if it breaks, it means that this branch point will go into your parallel region. So this will not be the saddle point. And well, this is just computation level, and you may ask any physics behind that.
Yeah, and I was asking, even at the level of computation, do you see a divergence or something like that?
No
approach.
No divergence. Just force equals not 0. The force equals some finite number, which force is not cancelled, which means that force is not cancelled.
No, it's not cancelled. So when you're at the edge of this, something special should happen. Meaning you've got a saddle point here, you've not got a saddle point there. Usually at the edge of such things, something special happens, right? Do you see any of that?
In the computation level,
No, you compute a determinant around this. Do you see something funny happening at the point at that?
so yeah, that has been appeared in some other paper. People consider on top of the black holes, consider distributing instantaneous configuration. You can consider it. So when distributing wraps three sphere on internal S5 and S1 in AdS5, you can compute the distributed action, and it will give you this. And meaning that if imaginary part is smaller than this, the black hole solution is unstable under the condensation of distributed instantons, and that is when this is violated. So
It's exactly your condition.
well, some part, not every part. I mean, so yeah, like this we don't know, but this can be understood as the distributed instanton.
Distributed instanton. It's okay.
We would like to modulate these conditions in charge space, right? Where exactly this.
In the microcanonical
Right.
ensemble,
And see something special happening.
That thing, I mean,
Yeah.
the same as the black hole instability.
I think it's not, right?
no. In the grand canonical ensemble, you can draw like this, and so this is the instability, right? Right? And our region covers completely. This is some parameter AB.
Yeah.
This is the Sporadian instability, right? And our settle only covers somehow this region.
So it doesn't reach the edge.
Yeah.
But what can you say a little bit more about this D3 brain instanton? What is that some sort of instability?
Yeah, I mean, you can consider on top of the black hole background, you can consider this brain wrapping these various circles in AdS5 times S5. They are the instantons in this background, and so basically you have
They get negative action, you're saying.
you have this classical settle point, and on top of them you can have some instanton configuration, right? So this is usually the non-perturbative corrections to our classical settle point, and the problem is that if it is larger than 0, then this vacuum is unstable, and this distributing instanton want to condense to and go to some another more more stable settle point.
And do you think that this is a chemical potential effect? Like, past the Hawking-Page transition, or one side of the Hawking-Page transition, for instance, this cell is no longer stable. But as a function of charge, it's just stable. I mean, is it that kind of thing? Or...
Yeah.
Oh,
In charge space, it is stable.
yeah, nothing's happening.
Yeah.
So it's just some problem with working in canonical ensemble.
Yeah, grand canonical ensemble. Yeah.
Let me just back up. I mean, you are doing the calculation essentially at weak coupling, right? Right? So they oscillate. Here's where I'm going with the question. In the very old days, people used to say, oh, index will equal the total number, because as you go from weak to strong coupling, everything that can pair up will pair up, And what I'm asking is, okay, you see these oscillations, but you're essentially at very weak coupling, right? Is there, as you go forward in your talks, is there any evidence that, whatever can pair up does begin to pair up, so that, in fact, the index may end up equaling the total number? Or is that...
I mean, some people believe that, but I don't think, we have any clear evidence really that happens. But well, in the tomorrow's talk, I will talk about cohomologies. I mean, operators responsible for this index. And normally what happens is that if you find some pairs in weak coupling and they become a pair and lift at strong coupling, so that maybe the index C really the degeneracy at strong coupling. But that I don't think we know very much about.
Just to say, if you believe our Gray Galaxy and DDBH papers and the supersmart, the paper we wrote together, that's not the case.
Yeah, actually, that is the counter evidence.
There are states all along this line.
Yeah. So
Even though there's no impediment in your strong coupling,
there's no representation theory.
Yeah, if we believe our supersymmetric galaxy is really there, then it means that even at strong coupling, you have pair of two charges, but which is not paired, even at strong coupling.
This is a matter of huge debate, right? The Chinese don't believe it. Zheng Yang doesn't believe it.
He has very much. Yeah, he very much complained about this. Why it's not lifted? But
I feel that at least for angular momentum, given because we have a representation theory argument, anyway, we'll see who's right.
Yes.
Okay, and just to understand, so the D3 instanton is just something you can actually check in the gravitation.
Yeah, gravity, right? Yeah.
And even though, even though there are no non-trivial 3 cycles on S5 or 1 cycle on S3, this instanton exists. Is it?
Yeah.
Because in Calabi-Gauss, where I know it, it's usually associated with non-trivial cycles.
Sure.
But not here.
Yeah. Interesting. Is it the Dolmer cycle? I see. And this is just
okay. And this you don't see this as a meaning. In charge space, you were saying that the formula just goes through beyond this point, right? So normally the way that works is that there were 2 saddle points. One becomes dominant, the other is not dominant. But you just stick with the non-dominant saddle point, because even though it was not dominant in chemical potential space, it was the dominant thing in charge space. You just work with this guy, forget about the fact that it was not dominant, and that gives you the right answer.
Yeah, actually, that is what we wanted to do, but yeah.
But that's not what you're saying, right? Because you're saying that saddle point stops existing. So how do I understand that in charge space, the answer is smooth?
I don't know. I mean, we are just thinking that ourselves, because it's maybe a computational limit. Maybe our cell point should be somehow changed beyond such region.
The channel point changes, but the answer remains endless.
Yeah.
Okay.
It's hard to imagine, but yeah.
Okay. And one last question. So now you changed the problem around in a way that won't change the answer.
Yeah, that's another point. So what will be the answer to the original question, and whether it will
be the same thing, right? It could be that that's completely different eigenvalue distribution, though it gives the same answer, because your theorem was that this potential and that potential have the same answer once you integrate. But there's no reason to expect that the saddle points will be the same, right?
Actually not.
They will not be the same.
Yeah.
Okay. So there's still the question of finding.
Yeah.
Unchanged.
Yeah, sure. And I think that kind of thing will give you more insight.
Yeah, because it's somehow nearer to what you're actually doing. This feels like this localization kind of stuff where you change the problem, you get the answer, but you haven't learned anything. You get the answer. Details of the configuration don't tell you what the details of the configuration of the problem you started.
Single function tells you and gets localized on instant terms. Yeah.
Well, what I'm saying is I want to know suppose I wanted to trace U to the end in the black hole diagram. So then I want to know what the eigenvalues were. Actually, is the problem.
Yeah. And for that original problem, we believe that not like this funny cell point, but linear distribution should work. And actually, we have some thoughts, but maybe after the talk I can tell you some stories. But anyway,
sorry to make sure. So I mean, the sort of instability due to the Euclidean 3-plane and so on.
Yeah.
I mean, in charge space, you are way past any kind of Hawking-Page transition, and everything is smooth.
It is smooth.
Also, by the way, the saddle point didn't really contribute to the energy, right? So even if it gets deformed, the free energy came from the first factor. So even if you kind of change it a little bit, as long as that doesn't compete with that.
Yeah. So let me summarize.
What do you say? It's the same again?
You were surprised that the saddle point may change, but the answer may remain another.
Yeah.
Right? Because the answer actually came from that factor.
You're saying it was not very sensitive.
Almost sensitive.
So let us summarize for today's talk. So we studied black holes, biggest black holes in AdS5 X S5 from the matrix model of organic phosphorus by Young Mills. So we constructed large cell points towards the black holes, accounting for the Beckmann Hawking entropy. And I explained some physics behind its branch point and stability condition against the discrete brane instantons. In addition, we found some multiple cell points, which are due to what we call the Euclidean black holes, and there are, this is also some other cell points of our matrix. And tomorrow, we shall investigate the biggest operators responsible for this Beckmann entropy, which are due to the black hole microstates. Microstates hidden inside the horizon, utilizing the language of Schwarzschild-Coulomb. This is all I prepared for the first talk. Thank you very much.
Okay, we have some time for questions.
I have a very general question, but let me wait because all of you experts should ask. I just want to come back to this point about index versus number of states, okay? Just so I internalize the lesson you're teaching us, because when I give a kind of public talk, I say, we thought maybe everything which can pair up will pair up, but then it's more complicated, and then Ashok gives this argument, in some cases that it really had to be bosons. But even Ashok will give all these kinds of caveats, when you actually talk to him. Okay, but you're suggesting something else. I mean, you're saying, look, it doesn't matter if it's bosons or fermions or bosons minus fermions, if it's all going like e to the n squared times something and all you're computing is that factor. Unless it's some very precise calculation, you'll get it right.
Yeah, leading order.
And this is a slightly new take for me. I
still think this is a miracle. I mean, why should this? Probably no reason why this should be, right? Or maybe I missed that.
Well, he's saying, look, it's like, I guess this is what he's saying. Yeah. And then I think, wait, let me just internalize it. Now, one of the two will be bigger. And it will dominate. And therefore, if you're not, but I guess you're not sensitive to the sign, right?
No, I mean, in some sense they are, because they get the cosine.
Yeah, sine can be extracted from the imaginary part cosine function.
Okay. Right. So what you will be getting is not the number of states. You're getting the index, therefore sensitive to the sign. But if you counted the total number of states, it would have been like where you're getting plus or minus, you would have gotten plus, but it would have still dominated. So I'll sign the 2 right? So this is a new take on why, right? You can do but you can do a relatively speaking trivial calculation and agree with, Bekenstein Hawking, right?
Yeah,
I mean, it's a very nice take, I feel. I mean, I think if I would give it like that, right? I just want to ask you folks,
This seems a bit fast.
This seems fast, okay. This says
Why generically and
Well, if there is B, then this is B.
So why are they different? Generically, maybe
Well, if you have some. If A equals B, then it means that you have precise cancellation between boson and fermion, and which means that you will have. I mean, that can happen, but
in supersymmetric theory, there's more likely that. Right?
This is non-BPS or BPS theory, and this is not for the non-BPS pair. This is BPS states.
I agree, but I'm saying one needs to be, because in supersymmetric theory, it's not like could be. I mean, the general condition might be as it could be. There not be an exact cancellation. Cancellation.
There could be some cancellation, and usually that happens. We have some kind of hidden symmetries between boson and fermions and some things, and actually that happens from the gravity.
Yeah, so there you go. You just gave an example.
This is a counterexample. For the graviton, this logic doesn't apply, but somehow for the black holes, it works.
I see.
It was more structure, I think.
I see.
Cannot be as generic an argument.
For black holes, many chaotic things happen, so
We have an appendix in our paper
Yeah.
on this question.
Oh, I see.
So this is the appendix that, assuming that the referee was Jen Bin, I don't think he agreed with. I'm pretty sure it is. But it's a very subtle question. In this context, states lie along a line, chances. So you can ask a more graded question to your question, not just bosons and fermions. We've got states at various points on the line. Okay, and then the question becomes: do you let's say that the number of states here is maximum sum of. Will you get your dominant contribution from near that next? Right, you've got e to the power n square states here, or e to the power n square states. And naively it might look that you will, except that when you do it, it's not the case.
Well, you don't, right?
Yeah.
Whenever you have
I
an
can
oscillation,
understand the
this
question, sorry.
No, I was just saying that in Shiraz's case, you are in a situation that you want to do, there's a bunch of states, right, that are contributing to the same black hole charge, right? And then you have to sum over all that.
Yeah.
Let's say you approximate an integral. Then you get an integral with an integrand which has a rapid phase oscillations, right? And when you have rapid phase oscillations, the right way to do the integral is to find new standard. That action usually has nothing to do with the kind of thing you will get if you ignore those rapid oscillations.
Yeah.
Sorry.
No, not at all. And one can try to make this, even just in the discrete case, sort of precise in the following way. You've got number of states here, and if you look between any two guys that are generically apart, one guy substantially dominates the other. But if you're looking exactly around the maximum, because things are varying very slowly around the maximum.
Why are we so
Because the maximum.
Yeah, maximum means the force.
Very large. But so let's say we're talking about just the DOM. I'm saying the same thing also. I'm saying that it's very dangerous then.
Yeah.
Because the norm is not dominated by one or the other around that, because the maximum is a maximum. And because of that, it's a very dangerous region. And now there are oscillations could play havoc. Because the stationary phase, station maximum amplitude is the same. The phase could do everything. Okay. And now we gave some argument about how we expect. Now, then there was a question about, anyway, I should shut up. It's a long story, but the question is, what kind of fluctuations do you expect for the number as you change your charge by order? And what we argued was that if you have random fluctuations in these numbers, okay, and this random fluctuation is larger than e to the power, the fluctuations are larger than e to the power minus n squared. If the random fluctuations are so small that it's e to the power minus n squared, that won't change anything. But if it's larger than that, then that will be enough to make your saddle point down. So the question of randomness is really important. That's why there's chaos, I feel. Whether the numbers at million and million plus one, on the average, of course, are the same, but there's some fluctuation. And whether that fluctuation is large, if it's large enough, what we proved is if the fluctuation is large enough, you can bound the fluctuation, you will have this dominance. Okay, if you've got some chaotic fluctuations, such arbitrary. And so
how much you need that fraction?
Anything larger, fractionally, anything larger than e to the power minus n. So, any power law would be good enough.
I mean, okay, on the black hole side, the fluctuations, shouldn't they just be determined by the entropy or something? I mean,
Yeah, their charges. Of course, their charge.
Yeah, by the charges, I mean, what I'm saying is that, let's see. I mean, the fluctuation should be down in n, right?
Should be down in n. The question is, are they so down that they e to the power minus n? If they're so down, then they don't explain anything. But if it was e to the power minus n, it's enough to show that this went down.
The maximum will.
So this was an observation we offered. How large the fluctuations are, I don't feel any.
So is it the same as saying that you will translate this? Can you translate this problem to an integral with oscillating phase?
Now, if for an integral, it's a little harder. I suppose you could.
And then you say that the phase is not proportional to the maximum parameter. It doesn't go like e to the n, e to the minus n, some imaginary part.
Add some noise in the integral, add some noise along the way. That will obstruct phase cancellation. That's basically it. What's happening?
No, but the noise has to be mean, when I say a function, it's a different value at different point, right?
Yeah, but there should be some chaotic noise. Yeah. If the number as a function of where you are along this line has a small chaotic piece that is not so small that it's e to the power minus n squared, then it can get rid of potential phase cancellations. That's the problem. Okay. Now, whether that is physically reasonable or not, I don't know. We can have lots of arguments. Yes. Okay, but this we proved. So now in the graviton spectrum, there is no chaos. So there's no cancellation. So the space is obstructed.
Yeah.
But the hope is that because black holes are more chaotic objects, there is this kind of fluctuation. But of course, it's just hope.
Yeah,
Which gender doesn't matter.
Yeah, I mean, this is a hope. We hope that the answer is correct. So,
but then, let me just make sure I want to tie what Shiraz said to what you were saying, which is in whatever mystical integral Shiraz was doing, how is it related to a n square plus minus e?
could I, if you don't mind, I'll
Yeah. You see, there's more fine-grained question than bosons are simple. Because the charges lie along the line. Okay, and there are a number of states at each point of this line. Okay, so there's some index. So it's e to the power n square times some function of, and then you're summing. Potentially there are signs. Okay, so that's the structure. It's either positive or negative, and there's e to the power n square. Now, where this f of I, forgetting about this. I'm not keeping track of the plus minus yet. That's the question then. But where this guy is a maximum is where you might expect it to dominate. And the question, if we could show that happens, then you would have explained why entropy is next. Okay,
that dominant may come with a sign.
Anyway,
Who cares?
And we know it does come.
Yeah.
Okay? So now the question is, in this sum, under what situation will it be dominated by this max? As Abhijit said, if there are generic fluctuations in the neighborhood of this sum, that could very much obstruct that thing. So our observation was that if there was a small amount of randomness in the number along this line, that could obstruct the phase.
But can you put that noise there in that expression?
Yeah. So let's say that we have this times delta phi, where delta is now a random quantity. Times that. With this, no, I think
that could just be part of that. Right? You don't want n square is front of that.
Yeah. I'm trying to remember. Would you remember, was it times that or upstairs? Upstairs.
Times is outside.
Yeah.
Outside.
Plus delta.
Yeah.
Plus delta phi up there, and then as long as that was not too small, then you can basically argue that this thing will always win. The maximum will win. But of course, there was a small place where if it was small enough, that will not.
Yeah, and actually from the graviton index, you see this doesn't work and this severe cancellation happens and this knife dominant term doesn't give you the answer.
And the last comment is that any calculation that was really in the vicinity will not have this chaotic fluctuation. Okay? So if you were doing on the set of various indices, it would not have the thing. But this is not a free calculation. Because this is the part that is not protected by field. This is the cohomology that's not the index. This is really the number of states here. Okay? Which felt like it could have some chaotic. But of course, basically.
If I just to understand your grounds of being a little cautious, I mean, suppose I could promote it to an integral on the real line and then say I'm going to do it on the complex plane. Then you do it, because there's at least an n square in front of the first term, you try to do it by stationary phase, right?
There's a minus. Let's say, let me take the worst case scenario where all the signs oscillate. It's here something, okay? -1. But now we have to, if you insert appropriate units, I would imagine that would get e to the I pi n squared. That sign, I'm modeling as e to the I by n square.
Delta I, right?
Yeah, instead of delta, I would put.
Yeah, that was always
Says n square times I square.
minus 1 to the power.
Then I would have just put plus I pi. I.
Yeah.
So
This is I by n
it's Z, right?
This is I by n square. Right?
Oh, this is I by n square.
So the appropriate.
Yeah.
So when you do that, then that if you write it in these terms,
Okay.
that would give you.
Okay. Now it makes sense.
Yeah.
Then
So
this is a rapid oscillation. The point is that in those units, very rapid.
yeah, the question was in the amplitude, is there also an oscillation? If there's an oscillation, let's.
But this is the amplitude, right? The real part will govern that.
Yeah, exactly.
Why are you worried about the real part which is subdominant? It doesn't do multiply.
But if this, you're saying that doesn't matter?
I was wondering why does it matter?
No, it matters because if there is an oscillation in that, it obstructs cancellation.
So you're saying that this integral dx e to the power k.
But this is much more subtle. Like that. It's still less subtle.
Yeah.
So real part of f of x, right?
Yeah.
Plus I imaginary part of f of x,
Yeah.
right? Now, so already the real part, that's the amplitude, right? This is the amplitude.
Yeah.
So it looks like that.
Why does it look like that?
Because there is a real part and there's the imaginary part.
Yeah.
The imaginary part oscillates a lot.
Yeah.
The real part, maybe this fluctuates a lot.
Yeah.
Right? Like this.
Yeah.
Now, you're saying that I add delta of x here, right? Which
Yeah.
is some fluctuation here.
Yeah.
Which doesn't even multiply k.
Yeah. It could be very small. Much
Yeah. So then
Why does it change anything you're
at
asking?
least in the saddle point, I would forget about this.
No,
Because it doesn't multiply this large number.
Yeah. But
And then I will find a saddle point here somewhere in the complex flow.
but the question is just this: that in the sum over numbers,
Yeah.
Okay, are the minus signs effective at making cancellations or not?
Okay.
Okay, and if there is enough fluctuation in this real part, you can show that it cannot be.
So if that is analytic function, you can approximate that summation and an integral.
Yes.
But if you have some like random.
Okay, so this step itself is not
Yeah.
working.
Yeah, no.
Yeah.
This was more.
If you have some like
But then I will
random.
That's true.
And it's a fluctuation on scale 1, not on scale n square.
Yeah, right. Next slide.
Next, yes. And it has to have some randomness. It's simple calculation.
Right, I know, but I was trying to understand from the integral.
Yeah.
That itself you cannot do.
Yeah. Okay, so that step itself is so random that whatever.
With the
So jagged.
sum to integral approximation is very dangerous.
It's very much like this point Witten made that, n
Yeah.
1 million and 1 million plus 1 might be very different.
Yeah.
In the large end.
I mean, there is sometimes people talk about some way of approximating such in sums also, right? Sums as opposed to integrals. Maybe that's the kind of technology used to show that.
All we did was we did very simple minded stuff. We could show the fluctuation. You just look at the expectation value of this, think of it as an ensemble, compute the expectation value, and so see when it is, the kind of stuff you guys love. But I want to say that if the fluctuation is smaller, there will definitely be something. But if the fluctuation is small enough, it cannot obstruct. That small was like e to the power minus n square. So if that was what you expect physically, I and that will be the argument. How large?
I mean, can one put it like this, that if the fluctuations are small enough that you could use an integral approximation, then it seems clear the saddle point will move
It
on.
will move off. Yes.
So therefore, it has to be so rapid that you can't.
Yeah.
Okay.
Yeah.
Right.
Yeah.
But it would be great if one can make this precise, that they're so great. The connection between chaos, which then justifies why Bekenstein Hawking should capture.
Yeah.
You do the index in a simple-minded way. It's given the spectral to scale. I mean, that would be great. You have the most beautiful thing.
In order to do that.
We have this nice appendix on the agenda, doesn't it?
Just give a talk. Maybe,
I mean, I'm assuming it. Some referee.
The referee's issue is about with this argument is correct, but he's saying that
If referee had an off-field coaching, you want to engage with the argument in our terms. Yeah, so, but I think it was ended because the referee had very perceptive comments. Pen selection. So, I mean, I take it seriously.
Yeah, strong belief that can be paired, should be paired.
That's a naive thing. But,
It was at the level where you cannot say one person's right or wrong.
I see. But maybe one of you can give a talk just so we understand. Yeah.
We actually propose this as a new criterion for chaos. People often say that chaos in supersymmetric states was chaotic matrix Fs. Our proposal was the number of states as a function of charge should also have chaotic fluctuations. So why not?
Or the Bose-Fermi nature.
Let's say there's just a number of states at a given charge in number of supersymmetric states because it's controlled by black.
but in particular, as a function of a given Gauss number, right? I mean, the charge will supercharge.
Yeah.
In that line.
Along this,
Yeah.
should be chaotic.
Yeah.
I thought number of states may be robust, but it oscillates between. For me,
No, but it's just that absolute number should also.
Oh, really? I see. So then there's no good limit at all.
Yeah, small compared to the leading one. Any power, 1 by n square, 1 by n to the 4th time, that would not change the leading order answer, but would obstruct the calculations.
Even if it were just bosonic, but changing by 1 over.
If it was bosonic, then there would be no cancellation.
So it's more the.
Let's take the worst case. The worst case is that you would have thought, in fact, in our paper, we looked at the case where the signs alternated.
Yeah.
Neighbor.
Okay.
So it would be as bad as you can.
So you're saying generically the signs will change.
Suppose the signs are changing.
Okay.
We're not going to take the cheap way. We'll allow the signs to change, and we want to see why this might work.
But is that really the worst case? Because it could be that 5, then 5, then 5, and 5, and then that chaos you have may become smaller in that 5 batches.
5 batches. At least a bad case, I don't know.
No, but is it? So maybe chaos remains.
Yeah. So very interesting thing happens in this index computation and black entropy thing, and I think this spatial cohomology will have reveal some nice features about these
if
things.
what we are saying is correct, it is basically the statement that beyond large n, nobody will ever be able to compute the code. Because it will be such a complicated function. I mean, the leading large n will be clear. And maybe but there will be some irreducible fluctuation which will not be humanly computed.
Although, I mean, the simple matrix counting problems, we know that there is some structure, right?
Simple matrix, like 183 PS, like that.
Yeah, that kind of thing. Not even 183 PS, not even the diagonalizable matrices, but the kind of things that Robert and friends have been doing in the matrices. They find very nice structure. They write down complete formulas for that, right? There's some structure. I mean, of course, it's far from the problem that we're talking about, but there's some moral sense.
Yeah. So
at least matrix relations don't seem to be capable of giving chaos. Chaos may come from the tree level
from the interactions, right here.
Yeah.
And just to ask us, sorry, very, please go on, but a very general question then, which is, okay, there's so much known about nearest neighbor statistics in random matrix theory, right? And if the issue is about nearest neighbor degeneracy or something, right? Nature, I mean, can you? And for random matrix theory is actually widely believed, right? That there's universality. It actually doesn't matter what kind of Hamiltonian it is, as long as it's chaotic. It's you have this tenfold way classification, right? And I mean, is anything known about supersymmetric matrix theories? And I mean, is there a parallel development there which you might hope to, tap into? I'm just asking this randomly because, I mean, for normal Hamiltonians, it's actually shocking how good, random matrix theory is, right? For nearest neighbor.
For the supersymmetric black holes, near horizon geometry is governed by super Schwarzschild modes and so on. So people have been working on that, but I'm not sure whether this random metric stuff.
I mean, this guy, I think Witten and Priyachi wrote the paper.
Yeah, they wrote some massive paper, right?
Just putting random matrices that had a certain amount of soups.
But that's a good place to see where there are these chaotic fluctuations. Because I imagine you would get exactly these types of series.
I was just wondering whether that bears out this idea of how big the fluctuations are. If it's bearing it out, then I mean, it really seems maybe there's even some universality that you'll always have this level of fluctuation.
Okay.
Okay, there are no further questions.